Welcome, everybody. So this talk came together a little last minute. So I was out getting my COVID vaccination this morning, first dose. Yay! So so it was a little rush putting it together, but I think I've got some perspective on just some of the places I've been and some of the things that certainly I think none of us could have predicted. You know, how the last year would play out, and in my case, it was extremely unexpected. And so I'll talk a little bit about that, but I just want to give a sense for, you know, generally my career has been, I loved math. I always wanted to do math things, and but I wasn't exactly sure what that would look like. So when I set out, I thought I would end up in academia for a very long time, and it just didn't work out that way. And in many ways, you know, I have been blessed and I'm grateful to have the career I've had, and it's been quite fascinating, and there's some really great things about it that I'll share. So also hopefully a few interesting stories. For the COVID stuff, I'll try to share what I can, but it's been still kind of in the middle of that, so it's kind of hard sometimes to step back and just take a look and figure out where exactly am I right now. So let's go ahead and get started. So here's my just kind of, you know, resume background, where I've been. So I graduated from Harvey Mudd College in 2000 with BS in mathematics. I worked with Francis Su, if I think many of you may know him, who went on to become the president of the MAA, and is well known. He recently published a book on, I forget the title with it, but yeah, if I come up with it, I'll let you know. But after that, I went on to Magdalen College at Oxford. That's where I spent some time as Rhodes Scholar. So a lot of cold, dark winters in England. And after that, I came back to the United States to get my PhD in mathematics at the University of Maryland. So first job after PhD was a postdoc teaching fellowship at the United States Military Academy. So that's where I got to know Brian. I moved in next door to him, and got to know them really well. And, you know, it was a fantastic experience. At the end of 4 years, I started looking on the job market for other places and settled down at the Johns Hopkins University Applied Physics Lab. And I'll talk mostly about kind of my experiences there, between different groups and different roles that I've had. And then most recently in the past year, I worked on the national COVID response. And I think somebody, looks like, shared the name of the book. Yes, Mathematics for Human Flourishing, fantastic book. So, all right. Too much. All right, so career one. You know, so this is kind of where I thought I'd end up. I loved math from, you know, as soon as I got to college, I was going to be a math major. I spent 4 years. I dabbled in physics a little bit, computer science a little bit, but I was quite certain I'd end up doing math forever. And so I wrote a thesis on Sperner's lemma, something in combinatorial topology, and then went on to PhD in a very pure math topic, trace diagrams and low dimensional topology. So I just loved math, and so anything about it, I would just sit in a room and think about theorems. I had endless pages of notes about all kinds of mathematical things, and it's just very enjoyable. So when I went on to the United States Military Academy, I still remember the job interview, sitting in the room across from, I think Brian was there, and Mike Phillips, who was the department chair at the time, at the math meetings in San Antonio. And you go through so many of these job interviews, and there's, you know, a lot of variety and a lot of really great places, and not too many of them actually stuck with me. But I think as soon as I left the table from this USMA interview, I was like, that's where I want to be, and that's where I'm going to end up. And I was quite certain about it, which was surprising because I'm not usually too certain about things like that. And so I started, you know, my teaching career there in 2006. And so I studied trace diagrams, which is this sort of topological algebra, sort of playing with diagrams, and some people just call it math by doodling. which was fantastic, and I really enjoyed it. But then I through various other parts of that career, I branched into some other areas. And so, part of the position was a joint appointment as a postdoc with the Army Research Lab. And under that umbrella, I worked on various things related to mostly teaming. So pursuit and evasion games, theories of cooperation, and some network science. Still very basic research, but it was an opportunity to branch out into some other research areas, some applied areas that was quite a bit different for me. The other thing I did is I kind of discovered that I really liked making mathematical simulations. At the time, I think Mathematica was just starting to get some really nice interactive visuals. And it was doing a really good job with that, but I kind of went down a rabbit hole with Java programming and creating fun things I could do with that. And so I've got one link here from that era. Hopefully it plays. I haven't tried this over a Zoom call. But basically the idea here was to kind of show different paths to pursuit and evasion problems, different solutions to this. So the basic of a pursuit and evasion problem is you have somebody, two players, and one of them's trying to run away from the other. And, as with any sort of mathematical problem, the more differences, the more variety, the more nuance you can add to it, the problems get more and more interesting. And so a whole sort of field of research and books are written about this topic. And there's a lot of really nice ways to visualize this. And just playing around with this, you end up with some very interesting, patterns. So here, what we're seeing essentially is, a steady state equilibrium that results from a simple pursuit and evasion game, where the equilibrium is shown here as that three-dimensional helix. So, I did a lot of things like this, basically just looking at different ways to visualize math, and it was a lot of fun. And I, had some wonderful students that humored me with this. I did some three-dimensional visualization, and one of my students actually gifted me with a collection of red and blue 3D glasses. And so we had, one of my favorite memories of teaching at West Point was having all my students wear these glasses in class while watching these sort of videos about three-dimensional calculus. So the whole time was fantastic, and I loved teaching. But when I got to the job search, then I ran into the location problem. And so I had some job offers, but they weren't in the places that worked for me. So I went a little bit outside, and that's how I ended up at the Applied Physics Lab. So the Applied Physics Lab is under Johns Hopkins University. It's what's called a UARC, or a University Affiliated Research Center. There's several of these around the country, and they're closely related to these things called FFRDCs, or Federally Funded Research and Development Centers. Essentially, they're national laboratories that focus on research and development in support of sort of national objectives, right? So national defense or other concerns. And so they're built up to support a variety of things, and they do all kinds of interesting work. So APL is one of those. It's I think the largest of the UARCs, although there's FFRDCs that are much larger. And we do a variety of things. So we have a big space department. We have had a couple space missions that we're primarily, the lead with. So New Horizons mission to Pluto got big in the news. Dragonfly is another one where we're looking at, I believe the idea is to use an octocopter essentially to land on Mars, but I could have the details slightly wrong there. We're also well known for the robotics prosthetic arm project. So there's a robotic arm that's in the news a lot. And then there's a whole bunch of things that we do that is kind of underneath the public eye, Navy systems, other kinds of defense systems, and so on. So APL altogether, we've got about 7,000 people. So a variety of backgrounds, lots and lots of engineers, a lot of mathematics as well as some even, lots of other technical fields. So primarily just a bunch of engineers working on a bunch of hard problems together. Our tagline is critical contributions to critical challenges. So what we're after is to make the best contribution possible to problems of national priority. So when I first got to APL, you know, this is not, you know, what I imagined doing, and I didn't know like anything about this world. And I was put in this group called Enterprise Knowledge Systems, and I had no idea what that meant. And to be honest, I still struggle a little bit with what exactly does that mean. You know, but through my early years there, I kind of discovered, well, it's kind of less about that and more about just how you go about solving the problems. So one of the things APL has in abundance is a whole bunch of interesting problems to solve. And that's where, you know, mathematics proves useful across a wide number of them. And even the mathematical way of thinking is extremely useful. So the ability to hit a problem that you haven't seen before, to understand, you know, what assumptions you need to make to be able to make progress on the problem and so on, is huge. And so one of the themes that I saw happen very quickly is when you start on down the road of getting a problem that may work out pretty well, you can very quickly end up, you know, in front of the front line, essentially, of people in the field. So one example I'd like to give is this project called Galaxy. And so Galaxy was a graph visualization problem. And I did some graph visualization at West Point. But APL at the time wasn't entirely sure that visualization on its own was useful. So what we did on that project was apply it to cybersecurity, essentially to look at how packets travel through networks, how communications travel through networks, and how those are connected to each other. And the hypothesis essentially was it is useful to look at how these graphs change over time and to analyze those and to make sense of how they change over time. And so, you know, it started small, but within, I think, 9 months, I was on a stage in Las Vegas. This is in the military, so it wasn't like a Las Vegas stage, but it sounds better to say a stage in Vegas, in a building on a military base that had a map with Area 51 on the wall somewhere. So remember walking by that map, and it was Area 51, and which is, if you want to know where it is, it's right next to Area 52. And I was talking about this project and basically showing a bunch of military officers how understanding cyber and the dynamic nature of connections between computers could be visualized in something that could be actually seen, not just in sort of this, you know, abstract concept. And so that resonated with them. You know, a lot of the military folks there had a background in the Air Force, and they were used to seeing where do planes go, right? And so they were looking, and that's why they had it in Las Vegas. They wanted to see where the planes went, except they wanted to do that for cyber. So that, I mean, it bubbled up very, very quickly. And I think that's emblematic of a lot of the problems that we get at the research centers, is that they can start small and very, very quickly become something that can have a very broad impact. And that, more than anything else, was kind of what surprised me about being at one of these R&D centers, which is just how quickly that impact comes up sometimes. So since then, I've kind of moved on and done some other things, a lot of visualization. You know, one of the tools I developed is called Dagger, which is, there's a little bit of public information about it, but you know, in a longer talk, I give some more examples about that. That one in particular took me to a desert in California with air-conditioned tents and barbed wire and other things, which is also very interesting work. I think the summary for me of the FFRDC and UARC work has been, you know, getting really, really great access to research problems, being on the front lines of people that use things. And then the other thing I'd mention about this is there's so many different people and so many different types of research, and there's many, many paths to success within this center. So I wanted to move on and talk a little bit about COVID. I'm in the middle of this right now. So all I can really say is how would I get into this project? And then I really, as I said, need more time to reflect on exactly where I am and what I'm doing, because we're in the middle of it and we're still working just huge number of hours in support of this national response. So the picture on the right is the great example, because it's really an example of why math led me into this particular project. So back in March and April, you saw figures like this being presented on the national news, saying that we have this bell curve shaped COVID transmission, and by June 1st, there's going to be 0 cases, right? And so as mathematicians, we know this is completely wrong, and we know many, many reasons why it's wrong, and we get a little worked up about it. And particularly when we see the uncertainty as visualized here going to 0 as you get into the summer, right? So there's something really, really, really wrong with the assumptions of this model. And so I was kind of offended by this personally. And so that was kind of early April. So late April, I got a call and somebody says, so do you want to come down and work at FEMA for a couple days a week? And naively, I said, sure, that sounds like fun. I would love to help out with the national COVID response. So early April, they said, okay, well, never mind a couple days. How would you like to lead the operations division, which is a 7-day-a-week affair? And I said, okay, sure, if I have to. And then June, they started this thing called the Data Strategy and Execution Working Group. And they said, oh, and by the way, at 7 a.m. This week, you're going to be briefing a cross-governmental team of about 100 folks about COVID and where COVID is worse in the country. And here's a list of 60 counties that we want you to go through in an hour. And so fortunately, that didn't last very long, but there have been a lot of curveballs and a lot of things on this project that have been just very challenging, but huge opportunities as well. So it's this balance between, as a mathematician or data scientist, you can have huge impact, but it's not free, right? It's a tough thing to go through and a tough thing to be involved with. And then recently, of course, there's something happened in January. The president changed. If some of you probably noticed that. And there's a whole bunch of stuff going on behind the scenes that I hope in future years to be able to talk about related to a lot of this. But at the moment, it's probably not the right time. So here's one figure that is out there in the public now. And so this is what we call our area of concern continuum. It's just an example of one of the products that we developed as part of this. And so it's really a combination of some really serious mathematical techniques behind the scenes. The magic there is that emerging hotspot dot was essentially a machine learning model that is looking to predict ahead of time where countries or which counties in the country might be burdened the most in the near future. So it's that in combination with some visualization to present in a figure, kind of the snapshot of where the country is. There's a whole much more I could go into on this, but I just wanted to leave with kind of 4 thoughts here as early reflections. Data science and math is absolutely critical to the national response. There's data flowing in from dozens of different places, all into one central location, and trying to make sense of that. Data science really are the heroes of the response, at least from the data side. I mean, they're heavily involved. Communication is critical. So a lot of the things I've learned about a public response is related to that. I've learned a lot. Public policy world is very, very different than a research world in terms of how you communicate findings and express them. Accuracy is critical, obviously, but that's just both numbers and assumptions and implications, such as the model I put out before. And the final thing I'll put out there is taking care of yourself is also hugely important, particularly when it's a heavily demanding environment. So given time, I think I'll leave it there and see if there's any questions, if I have time for questions.
Yeah, we have a couple of minutes. Heidi will be talking at the 11:55. So any questions for Elisha? I was asking, in terms of the COVID, what does the public see from your group? Are you reporting stuff for the public access?
Yeah, so we do a lot of public reporting now. There was a big push in December to start down that road. Before about December, they didn't seem to care too much about reporting publicly. But there's a lot out there now. So the CDC has a great website called the CDC COVID Data Tracker, and a lot of our work is up on that site or linked from that site.
Okay.
And they're constantly pushing to put more public data publicly, make more data publicly. So hopefully we'll have an API out there soon that will have, you know, some of our key resources that we use.
We're going to have a what? An API? What's that?
Yes, API. So that's a programming interface. So you'll be able to pull CSV files essentially from an endpoint
Okay.
URL, which will make it easier for people to use and reuse the data. So.